All right, let's get into it. Number 10, the axis of evil. In February 2003, NASA released the most detailed map of the cosmic microwave background radiation ever produced. The data came from the WMAP satellite, the Wilkinson Microwave Anisotropy Probe, and it was supposed to confirm what physicists already believed, that the faint afterglow of the Big Bang was essentially random, patternless, spread uniformly across the sky like static on a cosmic television screen. Instead, it showed something that had no right to be there. The cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang. At that scale, across billions of light years, the universe should look the same in every direction. The fluctuations in temperature should be random, with no preferred axis, no alignment, no pattern that corresponds to anything in our local neighborhood. That was the expectation. That was what every model predicted. What cosmologists Kate Land and João Magejo found instead, when they analyzed the WMAP data in 2005, was a large-scale alignment in the temperature fluctuations that appeared to line up with the plane of Earth's orbit around the Sun. They called it the axis of evil. The European Space Agency's Planck satellite confirmed it in 2013 with even higher resolution data. The alignment was real. Some analyses put the odds of it occurring by chance at less than 1 in 1,000. If the cosmic microwave background is a random imprint of the early universe, it should have absolutely no relationship to where our planet happens to be sitting. The fact that it appears to have one means either our instruments are contaminated by some effect we haven't identified, or the universe is structured in a way that places us in a special position. Both possibilities are deeply uncomfortable. Physics has no clean explanation for either. The axis of evil remains unresolved. It sits quietly in the data, confirmed by 2 independent satellites, waiting for an explanation that hasn't arrived. Either something is distorting our view of the entire observable universe, or the cosmos is, impossibly, oriented around us. Number 9. The cold spot. Those same cosmic microwave background maps contained a second anomaly, one discovered in 2004 and verified again and again in the decades that followed. Astronomers examining the WMAP data found a region of sky located in the constellation Eridanus that was measurably colder than everything around it. Not slightly colder in the way random fluctuations might produce. Significantly, stubbornly, inexplicably colder, by approximately 70 microkelvin below the average temperature of the CMB. To understand why this matters, you need to appreciate what the CMB actually is. It is the thermal fingerprint of the entire early universe, smoothed by 13.8 billion years of cosmic expansion. Temperature variations in it correspond to density variations in the infant cosmos, the seeds from which galaxies and galaxy clusters eventually grew. A region this cold, spanning approximately 1.8 billion light-years across, shouldn't exist under the standard model of cosmology. It is simply too large and too cold. Astronomer Istvan Sapudi and his team at the University of Hawaii announced in 2015 that they had found a supervoid in the region, a massive underdense area of space roughly 300 million light-years across. As CMB photons pass through voids, they lose energy and cool slightly. It was a promising lead, but when physicists ran the calculations, the supervoid was nowhere near large enough or empty enough to account for the full temperature anomaly. The numbers didn't add up. The cold spot remains one of the few observable features of the universe that sits in direct, unresolved tension with our best cosmological models. Some researchers have proposed it might be evidence of a collision between our universe and a neighboring one, a bruise left behind by contact with another bubble of space-time entirely. That idea has not been confirmed. It has also not been ruled out. ESA's Planck satellite confirmed the cold spot in 2013. 20 years of scrutiny have not dissolved it. It is colder than it should be, larger than it should be, and stubbornly resistant to every explanation science has offered. Number 8. The Hubble tension. Physics has two independent, well-tested methods for measuring how fast the universe is expanding, and they disagree. Not by a small margin that could be chalked up to rounding errors or instrument calibration. By enough that the global physics community has spent years eliminating every possible source of error and arrived at the same conclusion. The disagreement is real, and it points to something deeply wrong with our understanding of the cosmos. The Hubble constant describes the rate at which the universe is expanding, expressed in kilometers per second per megaparsec. When measured from the early universe using the cosmic microwave background, the Planck collaboration in 2018 arrived at a value of approximately 67.4. When Adam Rees and the ESH0ES team measured it from the local universe using Cepheid variable stars and type Ia supernovae as cosmic distance markers, they got approximately 73. Those two numbers should be the same. They are not. The discrepancy has now reached what physicists call 5 sigma significance, a statistical threshold so stringent it is used to declare particle discoveries at CERN. There is less than a 1 in 3.5 million chance the two measurements agree by accident. In 2023, Rees and his colleagues used the James Webb Space Telescope to recheck their local measurements with unprecedented precision. The tension did not shrink. It held firm. The Hubble tension means that either both of our best measurement methods are wrong in ways we cannot detect, or the standard cosmological model, the foundation on which modern physics is built, is missing something fundamental. Proposed solutions include new forms of dark energy, additional light particles in the early universe, or modifications to general relativity itself. None has been confirmed. When two completely independent methods of measuring the same thing produce irreconcilable answers, what does that tell us about the reliability of everything else we think we know? This is not a minor discrepancy at the fringes of physics. It is a crack running through the center of it. Number 7. Magnetars. On December 27, 2004, a wave of energy reached Earth from a dead star located approximately 50,000 light-years away. The burst lasted roughly a tenth of a second. In that tenth of a second, it released more energy than our sun will emit across the next 100,000 years. It was powerful enough to measurably affect Earth's upper ionosphere from the other side of the galaxy. The object that produced it was a magnetar, and physicists still cannot fully explain how something like it is even physically possible. Magnetars are a class of neutron star, the collapsed remnants of massive stars that have exploded as supernovae. A typical neutron star packs roughly 1.4 times the mass of our sun into a sphere about 20 kilometers across. Magnetars go further. They possess magnetic fields estimated at around 100 billion Tesla, approximately a quadrillion times stronger than Earth's own magnetic field. To give that number some shape, at the distance from Earth to the Moon, a magnetar's field would be strong enough to erase the data from every magnetic storage device on the planet. The December 2004 burst came from the magnetar designated SGR 1806-20. It was the most intense burst of radiation ever recorded from beyond our solar system. In April 2020, a magnetar within our own galaxy, SGR 1935-PLO-2154, was caught producing a fast radio burst, a discovery that helped solve a separate mystery about those enigmatic signals while raising new questions about magnetars themselves. Astronomers have confirmed fewer than 30 magnetars in the Milky Way, despite theoretical models suggesting there should be more. The physical mechanism that generates magnetic fields of this extreme magnitude is not fully understood. Standard models of neutron star formation do not cleanly predict why some neutron stars become magnetars and others do not. The energy sustaining these fields, the processes governing their behavior, the reason they occasionally erupt with such catastrophic violence, all remain areas of active and unresolved research. A magnetar is a natural object that, by every measure, should test the limits of what the universe allows. Yet they exist, scattered across our galaxy in silence, occasionally reminding us that nature is capable of physics we have not yet learned to explain. Number 6. The black hole information paradox. In 1974, Stephen Hawking published a calculation that changed physics forever. He proved mathematically that black holes are not truly black. They slowly emit thermal radiation, now called Hawking radiation, lose mass over immense timescales, and eventually evaporate completely. It was one of the most celebrated insights in the history of science. It also created, almost immediately, what many physicists regard as the most devastating unsolved problem in all of physics. Quantum mechanics rests on a foundational principle called unitarity. Information cannot be destroyed. Every quantum state carries information about how it came to be, and that information must be conserved, always. General relativity, equally well tested, holds that everything crossing a black hole's event horizon is irretrievably lost. If Hawking radiation carries no information about what fell in, and the black hole eventually evaporates entirely, then the information simply ceases to exist. That outcome is mathematically illegal under quantum mechanics. In 2012, 4 physicists at the University of California, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, sharpened the crisis. Their paper proposed what became known as the firewall paradox. To preserve quantum unitarity, the interior of a black hole must be separated from the exterior by a wall of high-energy radiation. But that firewall would destroy any observer falling through, violating Einstein's equivalence principle, which holds that free fall through a horizon should feel like nothing at all. Resolving the paradox requires either quantum mechanics or general relativity to be wrong. In 2019, 2 independent research groups, one led by Jeff Pennington at UC Berkeley and another by Almhairi and colleagues at the Institute for Advanced Study, independently calculated what is known as the page curve, suggesting information might eventually escape a black hole. The mechanism by which it does so remains completely unknown. Hawking spent decades on this problem. He died in 2018 without a resolution. Somewhere in the universe, black holes are methodically processing information that the laws of physics say cannot be destroyed, and we still do not understand what happens to it. Number 5. The matter-antimatter asymmetry. At the moment of the Big Bang, the laws of physics dictate that matter and antimatter should have been created in precisely equal amounts. When a particle of matter meets its antimatter counterpart, they annihilate each other completely, converting entirely to energy. If the universe began with perfect symmetry, every particle of matter should have found its antimatter twin in the first second of existence. The result would have been pure energy, and nothing else. No atoms, no stars, no galaxies, no planets, no life of any kind. The fact that you are reading this represents a violation of physics that science cannot explain. The asymmetry between matter and antimatter is studied through a property called CP violation, the slight difference in how matter and antimatter particles behave under certain transformations. CP violation was first observed experimentally in 1964 by physicists James Cronin and Val Fitch at Brookhaven National Laboratory using the decay of particles called kaons. The discovery was significant enough to earn them the Nobel Prize in Physics in 1980, but it immediately presented a problem. The degree of CP violation predicted by the standard model of particle physics is roughly 10 billion times too small to account for the matter-dominated universe we actually inhabit. For every billion antimatter particles that existed in the early universe, there were approximately 1 billion and 1 matter particles. That single extra particle in a billion is the entire observable universe. Everything that exists, every star, every atom, every structure of any kind is the residue of an asymmetry so vanishingly small it barely registered. The Large Hadron Collider at CERN has been searching for additional sources of CP violation since it began operations in 2008. no sufficient source has been found. Baryogenesis, the theoretical process that would explain how this asymmetry arose, remains unproven. Proposed extensions of the Standard Model, including supersymmetry and a mechanism called leptogenesis, have not been confirmed by experiment. The Higgs field, dark matter candidates, and various exotic particles have all been investigated as possible sources of the missing asymmetry. Your existence, every atom in your body, is the direct consequence of a flaw in the fundamental symmetry of physics that science cannot account for. Without that flaw, the universe would contain absolute nothing. What created it remains one of the deepest unsolved problems in all of science. Number 4. Dark matter. In the early 1970s, astronomer Vera Rubin and her colleague Kent Ford were measuring the rotation curves of galaxies, plotting how fast stars at various distances from galactic centers orbit around them. The expectation, based on straightforward Newtonian gravity applied to the visible mass of a galaxy, was clear. Stars at the outer edges should orbit more slowly than those near the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. Rubin and Ford found the opposite. The outer stars were moving just as fast as the inner ones, as if an enormous, invisible mass was distributed throughout and beyond the visible galaxy, providing the gravitational force that the visible matter simply could not. The idea of invisible matter wasn't entirely new. Swiss astronomer Fritz Zwicky had proposed missing mass in galaxy clusters as early as 1933, after calculating that visible matter alone could not provide enough gravity to hold the coma cluster together. But Rubin's work on galaxy rotation curves, published formally in 1978, made the case undeniable across hundreds of galaxies. The universe contains vast quantities of matter that emits no light, reflects no light, and absorbs no light. It interacts with normal matter only through gravity. We called it dark matter, and we have no idea what it actually is. Dark matter is estimated to constitute approximately 27% of the total energy content of the universe, more than 5 times the amount of ordinary visible matter. The leading candidates include particles called WMAPs, weakly interacting massive particles, and axions, a hypothetical particle originally proposed to solve a different problem in physics. Dedicated detection experiments, including LUX, Xenon 1T, and Panday-X, have searched for direct evidence of WMAPs using highly sensitive detectors buried deep underground to shield them from interference. None has detected a single dark matter particle. The Large Hadron Collider at CERN has found no evidence of the supersymmetric particles that were, for decades, the most theoretically favored dark matter candidates. One by one, the parameter spaces available to the leading theories have been narrowed, constrained, or closed off entirely. Dark matter's gravitational effects are undeniable and visible in the structure of every galaxy ever observed. Its true nature has resisted every attempt at direct detection for over 50 years. Something invisible, undetectable by any instrument we have built, and completely unknown to the Standard Model of particle physics, constitutes more than a quarter of everything in the universe. We know it exists. We can see what it does. And after 5 decades of searching, we have not found a single particle of it. Number 3. The nature of time. Write down any equation in fundamental physics, and you will find something peculiar. Almost every equation governing the behavior of particles, fields, and forces works just as well running backwards as it does running forwards. The laws of physics, at their most fundamental level, do not distinguish between past and future. They are, as physicists say, time-symmetric. Yet you can remember yesterday and not tomorrow. You can shatter a glass, but not reassemble one from its fragments. There is an unmistakable arrow pointing from past to future in every experience you have ever had, and the laws of physics cannot tell you where it comes from. The only physical law that provides a direction to time is the second law of thermodynamics, which states that entropy, The degree of disorder in a system always increases. Hot coffee cools. Organized things become disorganized. Time's arrow, in this view, points in the direction of increasing entropy. But this is a statistical law, not a fundamental one. It depends entirely on the universe having begun in a state of extraordinarily low entropy at the Big Bang. Philosopher of physics David Albert at Columbia University has argued, in his foundational work on the problem, that the arrow of time is entirely a consequence of this initial condition, what he calls the past hypothesis. But it offers no explanation for why those initial conditions existed, or what, if anything, enforced them. Einstein's theory of relativity deepens the strangeness. In the four-dimensional space-time of relativity, past, present, and future all exist simultaneously as fixed coordinates. There is no preferred now. Physicists, including Carlo Rovelli of the Centre de Physique Théorique in Marseille, have gone further, arguing that time itself may not exist at the fundamental level at all, that it is an emergent property arising from thermodynamic complexity rather than a feature of underlying reality. In 2018, researchers at the Moscow Institute of Physics and Technology claimed to have briefly reversed the quantum state of particles using a quantum computer, a result that remains contested and applies only to quantum systems, not to macroscopic time as we experience it. The block universe interpretation, supported by relativity, suggests that the past is not gone and the future is not unwritten. They both exist, equally real, as fixed regions of a four-dimensional structure. The sensation of moving through time, of experiencing a present moment, may be an artifact of how conscious systems process information rather than a reflection of physical reality. No experiment has yet resolved the question. No theory commands consensus. The one thing every human being is most certain of, that time moves forward, that the past is fixed and the future open, is the one thing the laws of physics flatly refuse to explain. We have built our entire understanding of cause and effect, of history and consequence, on a foundation that fundamental science cannot account for. Number 2, the quantum measurement problem. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions of the electron's magnetic moment match experimental measurements to more than 13 decimal places, a level of accuracy unmatched by any other scientific theory ever developed. Every semiconductor, every laser, every MRI machine, every solar panel works because quantum mechanics is correct. And at the absolute core of this triumphant theory sits a problem so fundamental, so philosophically devastating, that after nearly a century of effort, the greatest physicists alive cannot agree on what reality actually is when nobody is looking at it. The problem centers on what quantum mechanics calls the wave function. Before a quantum system is measured, it exists in superposition, occupying multiple states simultaneously. An electron has no definite position, no definite spin, no definite properties of any kind until the moment of measurement, at which point it appears to instantaneously choose one outcome from all the possibilities. Erwin Schrödinger proposed his famous cat thought experiment in 1935 precisely to expose the absurdity this implies. A cat in a sealed box, connected to a quantum device, would, according to the mathematics, be simultaneously alive and dead until the box was opened. The act of observation appears to collapse reality into a single definite state. But quantum mechanics provides no mechanism for this collapse, and no definition of what observation, or measurement, actually means. In 1957, physicist Hugh Everett at Princeton proposed the many worlds interpretation as a resolution. The wave function never collapses. Every quantum event causes the universe to branch into separate realities, each containing a different outcome. Right now, as you watch this, versions of reality are splitting and proliferating at a rate beyond comprehension. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, holds that the wave function collapse is simply what happens at measurement, but but refuses to explain the mechanism. Cubism, relational quantum mechanics, pilot wave theory, and objective collapse models each offer different answers. None commands a majority among physicists. A 2013 survey by physicist Maximilian Schlosshauer found no consensus on interpretation whatsoever. In 1964, physicist John Bell proved mathematically that quantum mechanics cannot be explained by hidden variables, properties particles secretly possess before measurement. Alain Aspect's experiments at the Institut d'Optique in Paris in 1982, which earned him the Nobel Prize in Physics in 2022, confirmed this experimentally. Reality is not locally real. Properties do not exist independently of observation. The theory that underpins all of modern technology, that has been verified to 13 decimal places, contains at its heart a philosophical void. Nobody knows what happens during measurement, whether the wave function collapses, branches, or does something else entirely, and nobody knows whether the universe has definite properties when unobserved. 100 years of the most successful physics ever practiced has left the deepest question untouched. What is real? The answer to that question, when it comes, will require a rethinking of physics more radical than anything since Einstein. Everything you are about to hear about the final entry on this list exists within a universe whose fundamental nature we cannot yet describe. Number 1. Dark energy and the accelerating universe. In 1998, two competing teams of astronomers set out to do something straightforward. They were going to measure how much the expansion of the universe was slowing down. Gravity, everyone agreed, must be decelerating cosmic expansion, and by measuring the precise rate of that deceleration using type Ia supernovae A as standard candles, they would nail down the ultimate fate of the cosmos. The High Z supernova search team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were not rivals looking for a mystery. They were rivals racing to confirm what physics already knew. Then the data came in, and physics broke. The universe was not decelerating. It was accelerating. The supernovae at the greatest distances were dimmer than they should have been, meaning they were farther away than any slowing expansion could account for. Something was pushing the universe apart, not just overcoming gravity, but strengthening over time, driving galaxies apart at ever-increasing speeds. Rees, Schmidt, and Perlmutter shared the Nobel Prize in Physics in 2011 for this discovery. The force responsible was named dark energy, and it constitutes approximately 68% of the total energy content of the universe, making it by far the dominant component of everything that exists. We have no idea what it is. The leading theoretical candidate is vacuum energy, the energy of empty space itself, sometimes called the cosmological constant. This is not a fringe idea. It is the simplest mathematical extension of Einstein's general relativity, a term Einstein himself introduced in 1917, then abandoned, reportedly calling it his greatest blunder. After 1998, it was reinstated. But when theoretical physicists calculate how large the vacuum energy should be, using quantum field theory, they get an answer that is 10 to the power of 120 times larger than the observed value of dark energy. That is a discrepancy of 120 orders of magnitude, a number written as 1 followed by 120 zeros. It has been described by physicists as the worst prediction in the history of science, the largest discrepancy between theory and observation ever recorded in any field of human inquiry. In April 2024, the Dark Energy Spectroscopic Instrument, DESI, released results from its first year of observations, mapping the large-scale structure of the universe with unprecedented precision. Its data suggested that dark energy may not be a constant at all. It may be changing over time. If true, that result breaks not just the simplest models, but potentially the entire theoretical framework built around the cosmological constant, deepening a mystery that was already incomprehensible. If the acceleration continues, galaxies beyond our local group will eventually be carried across our cosmic horizon, becoming permanently unreachable and unobservable. In the far future, even nearby galaxies will vanish from view. Further still, the expansion may grow strong enough to shred galaxy clusters, then individual galaxies, then solar systems, then planets, then ultimately atoms themselves, in what cosmologists call the Big Rip. The timing and the outcome depend on the behavior of dark energy over cosmic timescales, which we cannot predict, because we do not understand what dark energy is. Dark energy is not a mystery waiting to be solved with a better telescope or a more sensitive detector. It is a gap at the center of physics itself, written into the structure of everything, expanding in every direction at every moment, and the universe is accelerating away from our understanding, faster than we are closing in on it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.